We will first have a look at the ideal impulse train sampling. Let's assume that we have a signal in the time domain that might look like this and is called x of t. But now, instead of the continuous time signal, we want to have a discrete time signal, which we will call xs of k, where s stands for sampled. And we will do this by storing the value of the original x of t for multiples of the sampling period ts. To explain this mathematically, we introduce the pulse train or sampling train s of t, which is a train of Dirac deltas of height 1, which are ts seconds apart. Then we need to multiply x of t with s of t to yield the sample signal as a result. To understand later on how sampling can go wrong, let's go into the frequency domain and let's assume that the Fourier transform of our signal x of t is called x of omega and might look like this. Also, the sampling train has to be transformed into the Fourier transform. This yields the signal s of omega, which itself is also a pulse train in the frequency domain, but this time the pulses are omega s apart, where omega s is equal to 2 pi divided by ts. Since in the time domain x of t and s of t were multiplied to yield the result x of s, in the frequency domain x of omega and s of omega have to be convolved. So xs of omega will be the convolution of x of omega with s of omega. Remember that when convolving any signal x of t with a Dirac delta, the result is the same signal x of t but shifted to the Dirac delta. This works of course in the frequency domain. And here we are convolving x of omega with an infinite amount of Dirac deltas. So for each Dirac delta, we get a copy of x of omega shifted to the position of the Dirac delta. So we get the spectrum x of omega around zero frequency, around the frequency omega s, but also around all other multiples of omega s. So here we see that if we convert a continuous time signal into a discrete time signal in the time domain, this corresponds to converting an aperiodic signal in the frequency domain into a periodic signal in the frequency domain. Let's assume now that we want to reduce the sampling frequency, maybe to save some costs, and instead of getting xs, get now the new sampled signal xs dash, where the samples are now ts dash seconds apart, which is equal to 3 times our original ts. So instead of multiplying x of t with our original s of t, we now multiply with s dash of t, which is also a pulse train, but now with period ts dash equal to 3 ts. An expansion of s in the time domain corresponds to a compression of s of omega in the frequency domain. S dash of omega will still be a pulse train, but a compressed version, where instead of having Dirac deltas at multiples of omega s, the Dirac deltas are now spaced only omega s dash apart, which is equal to omega s divided by 3. So that now the copies of the original x of omega overlap each other to form the spectrum of the new sampled signal xs dash of omega, so that the spectrum will be the sum of all the different copies. And in this example here, this means that a lot of information is lost, since from xs dash of omega, we can't recover the shape of the original x of omega. In the time domain, this means that the samples are too far apart and information is lost. As a result, we will not be able to recover the original signal x of t from our samples xs dash. This is called aliasing, and when we sample a signal x of t, we want to avoid this effect. To understand how aliasing can be avoided, let's go back to the first example without aliasing. Assume that the signal x of t is band limited, which means that there exists a frequency 2 pi beta, such that x of omega is 0 for all frequencies above 2 pi beta and 0 for all frequencies below minus 2 pi beta. Hence, beta is the band limit of the signal x in hertz, and 2 pi beta is the band limit of the signal in radians per second. Then, in order to make sure that the copies of x of omega do not overlap in xs of omega, omega s has to be chosen twice the band limit of x of omega, hence it has to be greater than 4 pi beta. Or if you prefer the frequency in hertz, then Fs has to be greater than 2 beta. Converting this condition in the time domain means that Ts has to be chosen less than 1 divided by 2 beta. All those conditions are equivalent and they're called the sampling criterion. This is also called the Nyquist criterion. Unfortunately, many realistic signals won't be band limited, but will have infinite range and high frequency components. In order to sample those signals and minimize the aliasing effect, an anti-aliasing filter is used. This is an analog filter which aims to filter out the high frequency components so that the effect of aliasing is minimized.